Welcome to the Explainer. Today, we're stepping right onto the football pitch, but we're looking at it through a completely different lens. We're turning the pitch into a high-speed laboratory. It's a place where classical mechanics, fluid dynamics, and extreme human biomechanics all crash together in mere milliseconds.
Look, we've all jumped out of our seats watching those viral, miraculous goals that leave us absolutely speechless, right? But the core question we're answering today is this: are football's greatest goals magic, or are they just math? Are these jaw-dropping moments pure, unpredictable luck, or are they literally the millimeter-perfect execution of physics?
As the legendary manager Bill Shankly once famously said, football is not about life or death. It is more important than that. And you know, that perfectly validates the unbridled passion of the fans in the stands. But what's really fascinating is how science takes that raw emotion, that completely chaotic energy of the game, and makes it entirely predictable. So, let's look at the numbers behind the magic.
Section 1. The Magic of Physics.
Every spectacular goal you've ever celebrated, the swerving free kicks, the acrobatic leaps, is actually a highly controlled manipulation of physics. Now, to truly understand the perfect curving free kick, we first have to master this crucial aerodynamic principle, the Magnus effect. Basically, it's the curving of a spinning, spherical object to one side because of the uneven airflow generated around it. When a player strikes the ball off center, it spins. That spin pulls the air boundary layer along with it, creating a pressure difference between the two sides of the ball. And, as we probably all remember from high school physics, air flows from high pressure to low pressure, which literally pushes the ball sideways mid-flight.
Section 2. The spinning ball spiral.
Picture it. It's 1997. Roberto Carlos steps up to take an impossible free kick for Brazil against France. The ball bends so wildly around the defensive wall that the French goalkeeper, Fabien Barthez, is left completely frozen. It swerved so far out that a ball boy 10 meters wide of the goal actually ducked for safety before the ball hooked into the net. No way, right? Well, looking at the sheer data behind that strike, Carlos hit the ball off-center with the outside of his left boot. He launched it at an astonishing velocity of 36.69 meters per second. To put that into perspective, that's roughly 132 kilometers per hour. And crucially, that outside of the boot strike imparted an immense amount of counterclockwise lateral spin.
French physicists actually went and modeled this exact kick, and they discovered the secret to this spinning ball spiral. As the ball flies at that incredible speed, aerodynamic drag kicks in. Friction from the air slows the ball down. But here's the absolute secret. As the velocity drops, the spin takes over. The decrease in speed amplifies the Magnus force, pulling the ball out of a standard circular curve and forcing it into an exponential spiral that violently hooks back into the goal at the very last second.
So, Roberto Carlos used extreme spin to basically bend the laws of aerodynamics to his will. But what happens if you do the exact opposite? Let's bridge these concepts by comparing Carlos's high-spin exponential spiral with a completely different scientific phenomenon. And that is Cristiano Ronaldo's unpredictable, erratic, zero-spin knuckleball.
Section 3. Ronaldo's erratic knuckleball.
Fast forward to April 2012 against Atletico Madrid. Ronaldo delivered an absolute masterclass in chaotic aerodynamics from 35 meters out that left the keeper completely baffled. By mapping the frame-by-frame trajectory of Ronaldo's strike, researchers noticed something pretty wild. For the first 20 meters, it rises just like a standard parabola, peaking at about 3.3 meters high. But look at the final 15 meters. The trajectory completely breaks down. The ball drops rapidly and deviates completely unpredictably.
See, when a ball is struck with practically zero spin, you completely remove the Magnus lift. Notice the force vectors. The primary forces acting on a non-spinning ball are simply gravity pulling it downward and aerodynamic drag pushing directly against its flight path. Without the gyroscopic stability of a spin, the ball becomes incredibly vulnerable to the surrounding air.
As the ball reaches a critical speed, it experiences what fluid dynamics experts call the drag crisis. There's a sudden drop in drag as the airflow transitions from laminar to turbulent. And because a soccer ball isn't perfectly smooth, it's got seams and panels, the air boundary layer separates asymmetrically. This asymmetric airflow causes the ball to wiggle, shake, and drop erratically mid-air. So the goalkeeper isn't just reacting slowly, the ball is literally changing its physical trajectory multiple times.
Section 4. Biomechanics of acrobatic goals.
Okay, we've spent a lot of time analyzing forces in the air, but let's shift our focus back to the ground, or rather to the human body itself, and explore how players manipulate their own mass and energy. A prime example is Robin van Persie's legendary Flying Dutchman diving header from the 2014 World Cup. By diving horizontally, Van Persie completely reshaped the spatial dynamics of the play, intercepting a ball that would usually be way out of reach for a normal strike. By locking his neck and torso together midair, he significantly increased his effective mass. This allowed him to transfer maximum kinetic energy directly into the ball for a powerful shot, while simultaneously protecting his brain from acceleration-induced strain.
And then, of course, we have arguably the most acrobatic goal of all time, Zlatan Ibrahimovic's insane 30-yard bicycle kick against England back in 2012. We can actually break this masterpiece down into 3 precise biomechanical phases. First, the upward launch to overcome gravity. Second, the rotational torque midair. Zlatan essentially turned his body into a human pendulum, using the conservation of angular momentum to transfer effective mass straight from his core to his striking foot. And third, the strike itself. It's just a flawless, midair symphony of physics.
Finally, Section 5, Hawking's perfect penalty.
We've analyzed a lot of dynamic, moving plays. But what about the ultimate mathematical certainty in football, the penalty kick? It turns out even the late cosmologist Stephen Hawking dedicated time to finding the formula for the perfect, absolutely unsavable penalty. Hawking analyzed years of World Cup data and isolated these strict physical constraints. First off, target the top corners, as these are physically the furthest points from the goalkeeper's starting position. Second, the velocity of the ball must be exactly between 25 and 29 meters per second. Anything slower and the keeper has enough time to react. But anything faster dramatically increases the risk of inaccuracy due to minor errors in shoot-a-ball contact. And third, the player must use the inside of the foot with a 3-step run-up to maximize surface area and precision.
So the absolutely crucial point here is this massive number, 84%. Hawking's historical data analysis confirmed that when penalties are shot high into the corner, meeting these exact physical criteria, they result in a goal 84% of the time. Honestly, that's about as close to a guarantee as you can possibly get in sports. But why does this actually matter? What's the real takeaway here? It's that the flawless execution of Hawking's formula literally bypasses the human nervous system. When a ball is struck perfectly into those velocity and targeting windows, it travels toward the net faster than the goalkeeper's brain can even process the visual information, let alone coordinate a motor response and execute a diving save. It exploits the absolute neurological limits of human visual processing. You aren't just beating the opposing player, you are literally beating human biology.
Which leaves us with this final provocative thought to wrap up our explainer. Who is the true playmaker on the pitch? Is it the raw, unteachable instinct of the world's greatest athletes? Or is it the cold, undeniable laws of physics? Perhaps the true magic of football is simply that rare, beautiful moment when brilliant athletic intuition perfectly aligns with the mathematical certainty of the universe. Thanks for joining me today, and hey, the next time you see a top corner screamer, you'll know exactly the science that put it there.